Alright, so let us start. Last class we talked about the limits of the sequence. Actually, we talk about finite limit of the sequence, and then we see two examples where we find the finite limit, and then we see two examples where we show that the sequence do not have a finite limit, and then we see that if there is a limit, a finite limit for the sequence, then the limit is unique. So that is something we did last time. So at the same time, when we talk about sequences that do not have a finite limit, so we see an example of a sequence which is a sequence of n, and then we kind of see that the limit of that sequence is actually infinite. So it is possible that the sequence may have an infinite limit. So let us define what do we mean by limits of the sequence is infinity and how mathematically we can prove that, and then we will move on and talk about some other properties of the limit. So let me write down the definition. Right, so we say that the sequence tends to infinity, right, tends to infinity as n goes to infinity. Sorry. Okay, so we say that the limit of the sequence is infinity, right? As n goes to infinity, right? If for every positive number k, right, after some point the sequence, the components should be bigger than k, right? So that is how we say that it is the limit goes to infinity, right? So the tail of the sequence should be larger than certain or larger than all possible positive numbers, right? So that is the case. So it means the tail of the infinity will go to tail of the sequence will go to infinity, right? So we all know that. Right? So an example is this. Actually it is plus infinity, right? So when x goes to infinity, xn, sorry, yeah, right? So where xn is equal to n, right? So the sequence xn is actually n. So we can easily show that, right? So let k greater than 0 be arbitrary. So for every k you have to show that. So you take an arbitrary k, and then we need to show that there exists a natural number. Right? So since k is positive, right? So because k is a positive real number, right, by Archimedean property, we know that there exists a natural number such that that number is bigger than k, right? So then for every small n bigger than capital N, we get small n bigger than capital N, but capital N bigger than k, so small n bigger than k, for all n bigger than n. So if you combine all of them, right? So what you get, for every k positive, where there exists a natural number such that n is bigger than k, for all n bigger than n. So this is how we show that the limit of the sequence is positive infinity. Similarly, we can define for a negative infinity case, right? Right, so the opposite of this gives you the sequence goes to negative infinity case, right? So similarly we say that the sequence tends to minus infinity if for every negative case, right, you can find a natural number such that after certain natural number, the tail of the sequence will be smaller than that k, right? So you can see that. So for example, I will give you a pictorial interpretation, right? So if you look at minus n, right? You draw a picture. Actually, at 1 is minus 1, and 2 is minus 2, 3 minus 3. So the sequence will go to minus infinity, right? So if you draw a k here minus, you can see after certain number, right? So you put a k which is negative, then after certain value, the tail of the sequence is smaller than that k, right? So that is how we interpret the negative limit of the sequence is negative infinity, right? So example, so 1 minus n is actually negative infinity, right? So again, you can prove this by using Archimedean property. Right, so let me give you the hint of that proof. Okay, so again, you start with k being negative. Right? With k being arbitrary, right? Okay, so here's the idea. You want to show that 1 minus n less than k, right? So that is what you want to show, right? So actually, you want to show 1 minus n is less than k, right? For all n bigger than n. So actually, then that means, right? So let me show you the rough work. This is how we figure it out, right? Because actually you could have, because this 1 minus k, let k negative be arbitrary, but the reason why we choose this 1 minus k is because of the fact that, right, so this is the rough work of this. Right, so this is what you want, right? So this is what you want for all n bigger than n, right? But you know that capital N should come from Archimedean property. That is the idea behind this, and k is a negative number. It doesn't matter. You can say n greater than k as well by Archimedean property. There is nothing wrong there. But because you want to get this, right? So right. So but you want to get this for all n, small n bigger than n. So if small n bigger than n, then you know it is 1 minus n less than 1 minus capital N, right? So we need 1 minus capital N less than k. That is what you need, right? This is what you want to get for all n bigger than n, but n bigger than n means 1 because there is a 1 minus n. 1 minus n is less than 1 minus capital N. But you want this less than k, so you want this less than k, then is so you want this less than k. And if you want this less than k, this means you need 1 minus k less than n. That is why you choose 1 minus k there, right? Otherwise, you could have choose something else, right? 2 minus k also you could have choose. Or you could have say k. Why we need 1 minus k? Because question is about 1 minus n. So this is the rough one. This is why we choose 1 minus k. Right? So once we done this, then it is easy, right? And total will be k negative. There exists n belongs to natural number, such that 1 minus n is less than k. So then we have n. So limit of 1 minus n is negative. So that is how we show that the limit of the sequence is positive infinity or minus infinity. So I will give you a homework. Okay, so show that a to the power n, right, for a bigger than 1, right? So for a bigger than 1, you show that limit of a to the power n is positive infinity. Okay, so this is an exam homework. You can do it as you do the other two examples, right? So leave that as a homework. And now I go into a consequence of convergent sequence, and so that is called boundedness. Actually, a property of a sequence, it will be very handy in determining the convergence of a sequence. That is called boundedness of a sequence. So first one we talk about convergence. Now we are talking about boundedness of a sequence. Right? So here I will write down. Okay, so here we talk about boundedness of a sequence, right? So we call it a sequence is bounded about if all the components in the sequence are less or equal to some fixed value, right? If xn is less or equal to b for all n, then we call it bounded above, and if the sequence values of the sequence are bigger than a fixed number, then we call it bounded below. And if both sides are bounded, we call it bounded. Right? Both bounded above and below, then we call bounded. Right? There is an alternative way of saying boundedness. of the sequence is if you take the absolute value of the component, right? And if that absolute value is less than or equal to some fixed value for all n, then also we can say the sequence is bounded. So let me give you some examples. Okay, so 1 upon n, the sequence 1 upon n is bounded, right? Because you all know absolute value of 1 upon n is 1 upon n, that is less or equal to 1 for all n, so it is a bounded sequence, right? Right, absolute value of minus 1 to the power n is actually 1, right? It is plus 1 or minus 1, and if you put the absolute value, it is plus 1. So it is obviously less or equal to 2, right? Strictly less than 2 or less or equal to 2. So you can say it is bounded, right? So similarly, third one. Right, minus 1 to the power n over n is also bounded, so they basically it is a combination of both of them. So you can easily see that this sequence is also bounded, right? So these are bounded sequences. Okay, so now first section we talk about limit of the sequence. Now we talk about boundedness, right? So now combining both of them, let us define convergent and divergent. Now let us define what do we mean by convergent, right? So we will use the abbreviation CGT for convergent, but actually it is means convergent, right? And if the sequence has a finite limit, right, then we say that the sequence is a convergent sequence, right? Right, so what we do is we will say that if the limit x is finitely, then we say that the sequence converges to the certain limit, right? So that kind of sequence is called a convergent sequence. So opposite of convergent is divergent. The other one is divergent. Okay, so if the limit of the sequence is plus infinity or minus infinity, then we say that the sequence is a divergent sequence, right? So if the limit is plus infinity or minus infinity, then it is a divergent sequence, right? So you can see examples, right? So 1 upon n is an example, 2n minus 1 over n cubed is an example, and all these things are examples. So let's stick with the example we already did. Right? So that's n over b plus 1. So that's the example. So here you know that the sequence n 1 minus n, these are examples of sequences that are divergent, right? So they go to plus infinity or minus infinity. Then there are other types of sequences like this, minus 1 to the power n, right? Last class also I told you that these values will oscillate between minus 1 and plus 1. Right? So these are finitely oscillating sequences. In oscillating, there are two types of oscillation, right? So there are two types of oscillations. One is finitely oscillating, the other one is infinitely oscillating, right? So, for example, this one, plus 1 or minus 1, plus 1, minus 1, plus 1, right? Oscillation like this, from minus 1 to plus 1 to minus 1 to plus 1, right? So that is finitely oscillating sequence, right? The example is this, minus 1 to the power n. And so this sequence is finitely oscillating sequence, right? So that means the sequence, the limit does not exist. You can see you cannot put this under a tube, right? So you cannot put the tail under the tube because it is go between -1 and +1, -1 and +1, right? So limit does not exist, but it is bounded, right? So it is between +1 and -1, or it is between +2 and -2. Where absolute value is strictly less than some value, it is bounded, but limit does not exist. So that is called finitely oscillating sequence. Right? The other one is infinitely oscillating sequence. Right? So you can say we go to -1 and then you go to +2 and then you go to -3 like that. Right? So let me show you this. So you go from -1 to +2, +2 to -3, -3 to -4, -5, and like this. So this kind of things, again, it is oscillating, right? But infinitely oscillating. It is getting bigger and bigger and bigger. So this sequence also, you can see that you cannot put the tail inside a tube. That means there is no limit for the sequence, right? That's what I write. That does or do not exist, does not exist, right? It does not exist. Right? So the limit does not exist. At the same time, the sequence is not bounded as well, right? If sequence is unbounded and limit does not exist, then we say it is infinitely oscillating, right? So there are two types of oscillation. One is finite oscillation, other one is infinite oscillation. You can see that both of them do not have a limit, right? So they don't have limit. So they are not convergent or divergent, right? So that is important. You cannot say that is a convergent sequence or divergent sequence. So there are three types of sequence you can see. One is a convergent type that goes to a finite limit. One is a divergent type that goes to +infinity or -infinity, one of those, right? The third one is an oscillating type. It goes between two values, up and down, up and down, up and down, up and down, right? It will never go to a fixed value, even if it does not go to infinity. And you don't know whether it will go to +infinity or -infinity. It will keep on switching between plus and minus, plus and minus, plus and minus. So that is called oscillation. So there are three types of sequences you can categorize based on the limit, right? Or the convergence and the boundedness. Right. So now what we are going to do is we study about limits first, and then boundedness, and then by using the limit and boundedness, we categorize the sequences into convergent, divergent, and oscillation. Right? So three characteristics. So based on this, let us talk about some properties of the sequences, and we will define certain things and try to prove certain things under the properties of the sequence. So first thing is the relationship between convergence and boundedness. Right? So what can we say about the sequence being convergent and sequence being bounded? Is there any relationship between convergence and the boundedness? So that is our first theorem under the properties of sequences. The first property, write is a theorem, and convergent sequence is bounded. Right? So the first theorem, the first property is convergent sequence is bounded. The sequence, this, right? So if the sequence is convergent, right, then it is bounded, right? So this is what we are going to prove. We want to show that the sequence is convergent implies boundedness. So let us take proof. So let xn be convergent, right? So if this is convergent, then limit of xn, we can say L, right? So you can say L is the limit, and because it is convergent. So then you see for the epsilon positive, there exists n belongs to natural number such that xn minus L is less than epsilon for all n bigger than n. That is the definition for limit of the sequence is L. And so when we say limit of the sequence, we say that it is L, then we write the definition like this: epsilon positive, there exists n such that so and so. So now what we do is, first let's pick the epsilon. For simplicity, let me say epsilon is 1, right? I can choose any epsilon I like because this is true for all epsilon. So I say it is 1. If I fix the epsilon, then the n depends on the epsilon. So I can say there exists n1 belongs to natural number such that xn minus L is less than 1 for all n bigger than n1. Right? So you know that this is for all n bigger than n1. Right? But triangle inequality. You know this from the chapter 1 about the order properties. We studied something called triangle inequality. Right? So in triangle inequality we say that this inequality is true. So if we apply this, right, there exists n1 belongs to natural number such that so absolute value of xn minus absolute value of L less than 1. Right? So this is what we have. So now if you break this absolute value thing, right? So actually you get minus 1 less or equal to 50 less than absolute value of xn minus L less than 1. Right? So if you break this absolute value, you get this. Right? From this we take only this part of the inequality. So this says there exists n1 belongs to natural number that xn is less than absolute value of L plus 1 for n bigger than n1. So you get this, right? There exists n1 belongs to natural number such that absolute value of xn is less than L plus 1 for all n bigger than n. So you can see that now L plus 1 is a fixed number, right? You get absolute value of xn is less than L plus 1. So this is almost like boundedness. But unfortunately, here is the problem. You said this boundedness is true, or this boundedness is true only for the n bigger than n1, right? But for boundedness, you have to say it for all n. N is equal to 1, 2, 3, 4, for everything. You have to say xn is less than m. But here you can say this as m, but unfortunately, this is true for only n bigger than n1. So what will happen for 1, 2, 3, all the way up to n minus 1? or n1 minus 1, right? So you need to think about that. So here's the trick. So what I do is I choose my capital M, and I choose my capital M as a number which is largest among the numbers L plus 1 and absolute value of x1, absolute value of x2 up to absolute value of xn1, because those are the numbers I am missing in this inequality. And if I put this n, these numbers are missing 1, 2 up to n1, right? So I take all of those numbers and pick the maximum among them. Then very easily I get So then very easily I say xn is less than m for all n, because xn is less than maximum of that and L1. So combining all of them I get this. So this says this guarantees the boundedness of the, right? So clearly xn is bounded. So now the question is, will a bounded sequence converge? And so that is the question. So now convergent sequence bounded, that is true. If you have a convergent sequence, you can immediately say, okay, that sequence is bounded. Now is the converse true? Right? I will boundedness will not give you convergent, right? So that is important. Convergent give you boundedness, but boundedness does not give you convergent. So if you want to show something like this, right? Converse is not true, or some of the statement is not true, right? You can do it one by proving by contradiction, right? So that is one method which we did in several other examples earlier. There is another way to do it is giving an example, right? So that is also one method of showing something does not implies the other. Right? So this is called showing it by giving a counter example. Right? So an example that will show you that boundedness does not give convergence. That means we are going to give an example of a sequence that is bounded but not convergent, right? If you can show one such sequence, right, one such sequence which is bounded but not convergent, then that is enough to show that the converse is not true, right? So you don't need to prove sometimes. You can just give an example that contradicts the converse part, and that is enough. So here that is what we are going to do, because we have seen that example already, right? So in this analysis course, especially in most of the pure mathematics courses later on also, you have to give some counter example. So you have to keep your eyes open when you are doing examples, right? So we do certain examples for a reason. Right? So here is the example. So if you look at this sequence, we did this example twice. One is to show that the limit does not exist. We already did that, right? And also we show that this sequence is bounded today, right? So these two we already did. So that is why I am using that example again, right? So here the sequence is a bounded sequence which we already know, right? So we can easily show that. And we in the last class show that the limit does not exist. So that means this sequence is bounded but does not converge, right? So that is enough to show that the converse part is not true, right? So not always you will prove something, sometimes you will give a counter example to disprove something as well, and especially when you are trying to disprove something, giving a counter example also one of the easiest methods to see, right? So because if you remember, if you are familiar with lot of examples like this, you probably will see counter example and you can use it to disprove something, right? So that is one way of disproving. Right. So now let's see another property of convergence sequences. So I write this as a property 2. Right? For a real number a, right, xn plus a will convert to a plus l, and xn times a will convert to al, right? For the for a, right? So for some real number a, if the sequence has a limit l, right? So this is not a big thing, right? So you all know that, right? Right, so this is the definition of limit of the sequence being L, right? If L is the limit, you know that you can say for every epsilon positive, there exists n belongs to natural numbers, and that this is true. But what you want to get? You want to get a plus xn goes to a plus L. So here it is not a big thing. You can easily see that. And for the same n, for the same capital N and for the same epsilon, you can say that a plus xn minus a plus l, because in this you are putting a plus a and a minus a, so that does not change anything, right? So you can easily, okay, so you can easily see that that does not make a difference. So this is clearly limit of xn plus a is actually plus a, right? So this is quite clear, right? The second part, a times xn, right? So that you have to show. So I will leave that part as an exercise because a is 0 is nothing to prove, right? So this is first part. The second part, if a is 0, right? If a is 0, then you say the result is trivial because both sides you get 0, so there is nothing to prove, right? So other case, if a is non-zero, right? You can choose this. Then x is n belongs to natural number. Set that xn minus l is less than. So here for the epsilon, you choose as epsilon over absolute value of a, right? So you choose in place of epsilon, you choose epsilon over absolute value of a, because a can be negative as well. So you can put absolute value to make it positive, right? So that is the reason why you put absolute value of a is this, because we want to get axn minus al. This is what you want to get. Right? So this is actually absolute value of a times absolute value of xn minus l. Okay. So this is basically less than a times epsilon over a, because a is a, but xn minus l is less than epsilon over a. So when you simplify this, you get epsilon. Right? So that is why I choose epsilon over absolute value of a here, so that eventually I will get less than epsilon. So clearly we see that the results hold, right? Okay, so that is one property of convergence, that is when you are adding or multiplying a real number with a sequence, the limit changes accordingly, right? So you add a real number, you add the same real number with the limit, right? You multiply a real number, you multiply the same real number with the limit. So now what we are going to do is I will write down the next theorem and do the proof in the next class, right? Because it is about another interesting property of some thing. Okay. Okay. So here are the cases: adding two sequences, subtracting two sequences, multiplying two sequences, right? Multiplying two sequences and dividing two sequences. Right? So these are the cases. In all those cases, the limits also go the same. Right? So when you multiply the limits. When you divide the limits, and when you add or subtract, you add or subtract the limits. So I will do the proof in the next class, and then talk a little bit more about some other properties of convergent sequence as well. So I'll stop here and then continue tomorrow at 1 with the proof of this one. Let's stop here and then continue.